Okay, here we go. So solve for R. So that means get R alone. This is called a literal equation. So you're just using algebra. It's testing your algebra skills. This is the first problem on the review problems for today. So here we go. So once again, we title our notes 3-21. And here we go. So solving for R, what's my first step? Hurry. Good, multiply both sides by R squared. They divide out. Now what would you do to get R alone? Divide by F. So we have R squared equals G1, G2 divided by F. Then next, square root both sides of the equation. Root cancels out with power. R is equal to plus and minus the square root of G1, G2 over F. Now, we could write that as an answer, but technically considered not simplified, right? We want to be technical? Why not? We can rationalize the denominator. So let's think of this as R is equal to plus and minus the square root of G1, G2, all over the square root of F. So then we could rationalize the denominator if we were being really good. We'd multiply by root F, so that's not bad. We have on top the square root of G1, G2F, all over F. That would be the way advanced thinker style.
Wait, what was it?
Yeah, I'll scroll back up. This. Right here, solve for R. Okay, next problem. Go for it. How much mulch do you need to purchase to cover this grass, whatever mulch is? I think it has something to do with like basically fertilizer. I don't freaking know. Let's look it up on the internet. What? Okay, awesome. So for the fill-in, this one takes a little bit of thinking. This is a problem I saw. Remember, sophomores, you're needing to get a 4. Go for it. Nope. Good job. No, times sine, right? No, yeah, sine. Times sine of the angle in between. Angle in between. I'm just going to write sine of the angle. No, you have to know it. Question. How do we find the angle? Well, remember, it's the law of cosine. So this is testing to see if you can remember law of cosines and area. Go for it. Go for it. Go for it. That is a 3. Law of cosines, you gotta know. You gotta remember that because I'm not gonna be able to tell you that when you get to your stage test.
I got it.
This one, even though it takes a lot of time, it's not a time test, it'd be worth it to get it right, because it's definitely doable.
I'd say
I'd punch you in the face then. Because you're going to be that one sophomore. No, it won't. He's just teasing us. You better be. Yep. But that's why none of us will. Well, if you take this time seriously, you really shouldn't, because these are really exactly like what you're going to see. And you'll have to study before, but it'll be worth it. Yep. Guys, are we almost there? Because I'm almost there. We should be about the same. You guys are just as smart as I am.
Yeah.
You are. I got that. Yay! So the area of my big triangle came out to be that. My area of my small triangle came out to be that. Because you have to do area is equal to 1/2 times side 1, which is 10, times side 2, which is 12, times by sine of the angle that's in between. Yep, and then your small one would be, did you get 120 degrees for your angle? Okay, awesome. Your area would be 1/2 times 3 times 5 times sine of 120. Awesome. Okay, next problem. Write down the correct problem and then go back to it on your own time if you didn't get it. Well, you could just write it down on your paper and then make yourself a note that you didn't get it correct, and that's okay. I'm not going to mark it wrong. You get it right for trying, but you need to know so you can go home and practice that one. Go for it. Go for it.
It's gonna rain.
Did we get it? As quick as I got it? What they expect you to do, everybody listen, so you're not the common mistake. What they expect a regular student to do that's not in honors, they don't expect you to do this. They expect you to square both sides and then forget to square that. Yes, so don't do that. If you square both sides, it's the entire side squared. Okay, any questions? Okay. Next problem. Go, go, go. What? It says, what's the distance between the highest and lowest point? No, the answer is not 4. Right. It's that straightforward, you guys. Isn't our amplitude 4? Doesn't amplitude mean we bounce up and down between, our midline is between -4 and 4. So, very good. The distance would be 8. That easy. Don't make it harder than it needs to be. Okay. Write an equation for the sequence. So you're going to have to say, is this arithmetic, is it geometric? And you're going to have to remember the formulas for those. Or just think about it. No, you mean for this end of test? Yeah, we learned a lot this year. So let's talk about this one, everybody. Are you writing it down? Listen, what's happening? So on top, are we adding 1? Yeah. Adding 1 on top, and on bottom we're adding 2. So it's arithmetic, isn't it? So we'll think of it in sections. So the top, you'll say it's an arithmetic sequence. So what we would do is say, we know that for arithmetic, we would have a sub 1 plus n minus 1 times the common difference. That's the formula, the explicit formula. Remember that? Yeah, our common difference on top is 1. So our a sub 1 is our first term, which is 2. Then we're going to have plus 1 n minus 1 times 1. Does everybody understand? Yeah. And then we have, so simplify that, that'd be 2 plus n minus 1, right? Everybody? Yeah. Distributing. Now let's combine like terms. N plus 1, correct? So on top, the formula is n plus 1. Now on bottom, which n stands for like we take our terms and add 1. That makes sense, right? N plus 1. Okay, on bottom, we would start with 5. So 5, and then our common, so then plus n minus 1 times by our common difference, which is 2. So now distribute that through, ding, ding. So 5 plus 2n minus 2, combine like terms. 2n plus 3. So on bottom we would have 2n plus 3. So that would be our answer, yeah. Now look, does that work? If we plug in 1 for n, which would be our first term, do you see how it gets us to 2/5? We plug in 2, it gets us to 3/7. Do you guys see how that works? That one was hard because you had to remember this. So you gotta study it when you go to retake, before you take this. Did you write it down at least? Everybody? Okay, go. There's an easy way to do this and a hard way. Actually, honestly, it's almost easy just to sum the first 10 terms. I don't know. It just depends. Like if you can remember the formula for sum, then that's great. But if you can't, wouldn't it be worse to get it right to just write out what the 10 terms were and then add them up in your calculator? Yeah. I'd probably do that too myself because it's only 10. Yes. You'll use your own calculator. Yeah. So let's see if you guys can come up with the sum. Hurry and do it. And then I'll just write down the answer. Sum of 10 terms will be equal to a sub 1 times 1 minus r raised to the n divided by 1 minus r. So we can plug this in. Our first term, the sum of 10 terms, is going to be a sub 1 is 1/2, right? And then 1 minus 3/2 raised to the 10 power divided by 1 minus r is 3/2. And now you've just got to make sure to use parentheses. That's going to be what our sum is. It's just, can you remember that formula? If not, you would literally just write out the 10, make sure you have 10 terms, and then add them up in your calculator. It might be worth it to spend 10 minutes on the problem and get it right. It would be. It would be worth it. You have unlimited time, so it would be worth it for you to just spend your time and get it right. Okay, so I'm just going to write down the answer. You said it was 56.66. Or 58,000. Oh, 58025 over. I like that better because it's exact. Make sure you all type it in. What's very common is people forget parentheses and stuff. You got something different? So maybe they're wrong. You got what? They think they got it? Oh, you got that? What? Yeah, but what's going on? Don't plug it in all at once. I can't tell where you plug it. Oh, you're adding them up. You're adding them. You have to write out every single one of them somewhere. You're going to do it by half. You can't just times by 3/2. Yeah. Does that make sense? You're finding the 10 terms. We gotta find the sum. Does that make sense, Holly? Okay. Okay, awesome. Okay, go. Next one. Do it. Quick, fast, and in a hurry. Draw in standard position. So on your computer, you're gonna see like this, and yeah, an XY chart basically. Draw things that are degrees, then I don't have to think about it. So how do we convert from 8 pi9 to degrees? Yep. Yeah. 180 over pi actually, because you need the pi's to divide out. So that's 160 degrees. Yeah. So we can multiply by 180 over pi, because I like graphing degrees better, which is 160 degrees. So you go ding, ding. And what you would do is you would literally be able to, on the calculator, click and drag over to 160 degrees. All good? All right. Radius of 3. So if I said to you, graph this polar equation, this one's an easy one, correct? R equals 3 means we have a circle with radius 3, everybody, right? Yep, so notice I'm going to give you these polar grids already drawn for you, which is just an XY part, so just keep that in mind. Here's y, here's x. But now we're going to think of it as r theta. So we have a circle with radius 3. So we would go out 1, 2, 3, and there we go. No matter what theta is, so this would be 0 or 2 pi, correct, everybody? Right? Everybody? Pi 6. And so we can just go around. This is pi halves. It's going to still be a radius of 3. So I'm just drawing in my points here, and then I'm going to connect them. It's just a circle, so really I could have just gone like this. And we've drawn in a polar equation here. Pretty easy one. Okay, next one. Everybody paying attention. I'm trying to make this easy for you. So I said you graph this polar equation. That means theta equals pi thirds no matter what, correct? Everybody? So looking at this, once again, I'm just going to draw this in. So pi thirds, it's going to be always on pi thirds, which is right there. So no matter what, our radius can be whatever, but it's always going to be at pi thirds. So we have this straight line here. You see how that's pi thirds? Okay, cool. So we just draw this in. Polar equations. Notice they're going to be symmetric. You see how this is symmetric? Like we can reflect it and it's symmetric. Polar equations still symmetric, right? So here is the thing. All polar equations are going to have symmetry. That's going to be helpful to us because once we know a part of a graph, we can just then, because of symmetry, draw in the other side of the graph and not have to plot so many points. So what we're going to do is we can test for symmetry using algebra. So if it has symmetry, if it's an equation and it has symmetry over the pi halves axis, what we can do is we can take our r theta and replace negative r, negative theta. So we're going to plug in negative r, plug in negative theta, then we're going to simplify it out. And if it comes out the same as the original equation, then that's the symmetry. It would be symmetry over pi halves. So for example, if I knew this half of the graph, and I knew there was symmetry over pi halves, I could then just draw in this side of the graph, which would be nice. Everybody understand? Okay, so then symmetry over the polar axis happens if we have an r theta and we plug in r negative theta. So if you keep r as r, but then plug in a negative theta, you go through and simplify it, and it comes out the original equation, then it has symmetry over what's called the polar axis, which remember the polar axis is just the x-axis. So that means if we have the top half of the graph, we can then just draw in the bottom half of the graph because of symmetry. And then this one we don't get into as much. So symmetry over the pole, what that means is like if you have a bunch of points up here, like that tangent one, it's going to have symmetry down this way. So if we had a half circle like this and it had symmetry over the pole, then they would also come down like this. And that we can find by plugging in, if you plug in negative r, just regular theta, and simplify it, and you get the original equation, replace r theta. Yeah, so the original function is what we want to come out. Then that's what it has symmetry over. Yes. Yep, we just plug in negative and then we'll simplify it. So like, you'll see what I mean by simplify. Well, they all have symmetry. It's just which do they have symmetry over. So it's going to be one of the few. The polar axis means the x-axis. It's just called the polar line when it's in polar coordinates instead of x. So fun fact for you, you're going to see though, we're going to do it, but sine has symmetry always. So sine has symmetry over pi halves, and cosine has symmetry over polar. And you'll see why in a second. Over the polar, and then not over the pole. The pole, what's the pole? That was like this one. See how tangent we graphed it? Do you see how we just have, it's not over the particular axis. It's like they reflect this way across from each other. So like if we had a line over up here, and they'd come down here. Kinda, yeah. Yeah. Hey, we all good? What time is it? Okay, let's grab this first one. Whew, here we go. We can do this. Whew, okay, so I am, because I've never taught this and I've never felt like a little confused about something before I came to teach. Okay, so let's look at this. This one's pretty easy though. So we're graphing r is equal to 3 sine theta. We can do this a couple of different ways. First of all, we can think of what it looks like out on a graph. So not in polar. Does that make sense? Not in polar, just as an xy coordinate. So I drew it out for you. Maybe draw that out because really Mr. Roberts is having his kids draw it out every time. on an axis because it helps you plot points and kind of see what's happening when you put it into a polar graph. So think about sine. Our amplitude's up at 3, correct? Think of just regular graphing sine. And then remember for this one, our period is 2 pi divided by b, which our b is 1. So our period's 2 pi. So that's how I knew to go over 1, 2, 3, 4 tick marks. That's 2 pi. Then I split up my x-axis accordingly, and then I graphed sine. Remember, sine is 0, max, 0, min, 0, and so I drew it in. Now, obviously, we could keep plotting points, but I'm going to start here, and then I'm going to use my graphing calculator, and then I'm going to just kind of fill in what I need to fill in. Okay, so at 0, so now we're going to put this in polar coordinates. Now, notice I put theta first r, even though it's technically r theta, just because we always go theta first. Does that make sense? And then go out r. So when my theta is 0, we're up at 0. So let's plot out our theta. When we're at pi halves, my function then grows up to 3. So at pi halves, we're up at 3. And we start going down, 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 till we go back at pi, we're back to 0. Correct? Now you have to remember that this is a negative r, and it's negative r, but it's how it works you'll see in a second. Anyways, so then at 3 pi halves, we're at negative 3, correcto? Okay, 2 pi 0. So let's graph that right now. So let's graph that. So at 0, we're at 0. Now sine always starts at 0. Think about sine. It always starts at 0, correct? I didn't draw that very good, but it's okay. So 0, 0. Plot that point. Now we're going up to pi halves, so go up to pi halves. Now technically, between 0 and pi halves, aren't we increasing up to 3 slowly? Everybody? So at pi halves, we're up at 1, 2, 3. But to get up to there, we were increasing slowly till we got up to 3. Yes. Now after 3, aren't we then decreasing back down to 0 slowly? Our radius. So look, my radius is 1 right there, correct? So do you see how like up a little bit less is out at maybe 1? Radius of 1. How does it work? You get what I'm saying? Okay, let's look at our unit circle then. At pi 6, where's our radius for sine? 1/2, correct? Let me erase. Guys, do you know what we're doing? Plotting points?
No.
So we're plotting points. That's it. Okay. So maybe we just need to plot points in between. So let's plot some more points. So write theta r. At pi 6, so type it, like think about this. So it says 3 times sine at pi 6. So what's sine at pi 6? 1/2, correct? So 3 times 1/2 is 3/2, which is 1.5. So let's go up to pi 6 and go out a radius of 1.5. Wouldn't that put me there? That's a better graph, being more accurate. Does that make sense? Now we could do another point, maybe pi thirds for kicks and giggles. So let's do pi thirds as well. So everybody think about it. So go to pi thirds. So sine of pi thirds is √3/2. Let's type this one into our calculator and get a decimal since it's easier. So you'll type in 3 sine of √3 divided by 2. Let's do decimals. It's easier to graph radiuses as decimals. So 3 sine of... Now your calculator should be in radian mode. Sorry, you'll type in 3 sine of pi thirds, right? Okay. Okay, 2.6. So now we're going up to here and out 2.6. Does that make sense?
Oh, yeah.
So do you see how it's connecting like this, Sarah? And then finally up at pi halves, we then reach up to 3. So we're really just plotting points. Does that make sense? I just skipped the in-between ones. Yeah, you follow the curve. Does that make sense? Creating that pedal. No, yeah, I should have probably seen, that's why, like I said, I've never taught this before, so I'm learning what confuses and doesn't confuse people, because I could just see it. Does that make sense? Perfect. Okay, I'm glad you asked that. So now, after we reach 3, isn't our radius decreasing, but it's still positive, correct? Decreasing, decreasing, decreasing till we hit 0 at pi. So let's go over to pi, and then aren't we back to 0 here? So it was decreasing, decreasing, decreasing till we hit 0. We're drawing a rough sketch. I should have come out evenly. So this should have been like You know what I mean? It's symmetric because sine is symmetric over pi halves. We could get into why in just a second. Yes. Yeah, we're doing really rough sketches here. So then place this over more right here. Do you see how they're symmetric? No, this one we won't need to. Okay, now let's keep going because more happens here. So now let's go to 3 pi halves. So let's think about it. 3 pi halves would put me down here, correct? Now aren't we at negative 3? Which is back up here, isn't it? Because remember how polar coordinates work. Negative radius means walk backwards. So then that puts me back up here. So it's just a circle around that again. So that's our only thing. We have that. That's it. Wait a minute. So if we plug in negative r, negative theta, and so we simplify it down and it comes out the same as the original function, then it is symmetric over pi half. So let's plug in negative r is equal to 3 sine of negative theta. Well, now you have to remember something. Sine is odd, so remember that sine of negative theta is the same thing as negative sine of theta, right? So continuing to simplify this. We have negative r is equal to, we can pull out the negatives, so negative 3 sine of theta. Now to solve for r, divide both sides by negative 1. So we get r is equal to 3 sine theta. Do you see how when we plugged in negative r, negative theta, we get the same thing as the original function? So it is has symmetry over pi halves. So if sine had for example, we have this, then the other side would be this. Does everybody understand? And that is there are heart graphs. It's cute. We're on the topic of love. What part don't you? It wouldn't be. I'm saying if we had a function that happened to be a heart on one side, that curve, because there are those kind of functions. Yeah. Yeah, there is. Yeah. Okay, yeah, let's do one more. Let's graph cosine. Here we go. So we're graphing r is equal to 3 cosine theta. Oh, no, wait. I wanted to show you. I can now check my polar equation by using your calculator. And Amelia was kind of helping me out with this, but we are going to be using our calculator for a lot of this. So everybody go to your calculator. Now go to mode. Hey, why are you doing this? Go to mode. Now we're going to put it in polar and degree mode, because isn't it easier to see where a degree is on a polar axis than having to think about radians? In my book it is, in my opinion. Yeah, it'll graph as a polar equation for us. So now hit graph. I can't remember how we ruined it again, but we can look at the table of values. So look. So the table of values here, do you see how at 0 we're at 0? At 30 degrees, we're then at 1.5. Oh, here's what else we have to fix. The table set, everybody. Yeah, that's true. Okay, go to y equals, type in 3 sine of theta. Just x. See x t theta, it just means because you can even graph parametric functions on here. What do you mean? You hit the 3 button on your calculator. Just 3 theta. Now, go to table set. No, second table. You have to get into table set. And notice I wanted to see mine in degrees. And I wanted to get my intervals to be in 30 degrees, just because that's kind of what we've been doing around the unit circle. So my start point is at 0 degrees. And then table set is at 30 degrees. That just means it's going to work in increments of 30. Yeah. So hit second window. Yeah, me either. For some reason, I can't remember why, but you can look at the table of values. Second what? Second table. Then 0 and 30, just so that our degrees are working in increments of 30 degrees. Yes. I don't know. No, he said, who should he ask her from? Okay. So now you can see what your graph's happening, and then once you get to 150, it's, anyways, and so on. Yep. Now remember what negative radius means, guys? That you just walk backwards. You can't forget that. That's what confuses people. That just means you have to walk backwards. That's how equations work for polar. So if I say go to 150 degrees and walk backwards, you would end up over here. A negative radius. That's just walking backwards. You still go to that place, but then you just go, instead of out 3, you go back 3. Yeah, okay, let's graph this one. 3 cosine of theta. Once again, it kind of helps to have an actual graph. Mr. Runs fast graph out these. So think about describing this normally on an XY chart. Our amplitude's 3. Cosine for our period will be 2 pi divided by b. So period is 2 pi for this. So I went over 1, 2, 3, 4 tick marks, put me at 2 pi. And cosine starts at the max, 0, min, 0, max for cosine, remember? So it didn't. So now we can draw in r and theta. So theta is, when theta is 0, we start out at 3, correct? Look. Then when we go to pi halves, yep, when we go to pi halves, then we're back to 0. Now, once again, it's kind of nice to see what's happening in between there, so maybe I should have plotted some more points. But getting, the radius is getting smaller, but in positive, right? Look, isn't the radius getting smaller? Okay, so we can think about it. Then at pi we're out at -3, which you have to remember what that means. And then at 3 pi halves, we're back to 0. And then at 2 pi, we're back out at 3. So let's start graphing this very carefully. It kind of is a lot to think about. So at 0, we're out 3. So at degree 0, we go out 3 units. Put your first point. Now our radius is getting smaller, but it's still a positive radius, right? Look, right here's positive radius. Isn't this -2? I mean, 2. So it's going like this, like this, like this, until it hits at pi halves. So go up to pi halves, and then we're down at 0. Then at pi, so watch Dylan and Tyler, since this is what your question was. Then we go out, that wasn't it was more like this, like more circly. Then at pi halves, so everybody point your direction at pi halves, we're going -3, look. So that would mean going back here. So it doesn't have to put me back at the same point. Because that's what -3 means, is walking backwards. Does everybody see I'm back at +3? And then what happens is what happens after that, let's keep going. So then we're decreasing. Now, increasing, let's see, where was I? Oh, okay, go to 3 pi halves of 0. Okay, boom, that's there. So 3 pi halves of 0. And then back at 2 pi, we're then at 3. So we increase back to 3. So it makes a circle. Now, cosine is symmetric over the polar axis. So once we knew the top half of the graph, we could have just plotted in the bottom half. Does that make sense, everybody? Because cosine, yep. And we could get into why. How do we know if it's symmetric over the polar? If we plug in r comma -theta, is that right? Look back at your notes. I don't have that memorized. So it's it's symmetric over the polar axis if we plug in -theta and get the same thing. So let's do that. So we have r is equal to 3 cosine of -theta. So now simplify it. R is equal to 3. Cosine of -theta is the same thing as cosine of theta, right? Because cosine's even, remember that? So we get the same thing. So once we knew this top half of the graph here, it would have just been nice because we could have just now graphed in this bottom half. Type it into your calculator to make sure your equation looks right. That's what's great about this, is you're going to have a calculator on your test. You're going to know for a fact you got it right or wrong. Okay, go. Type it in. 2 cosine of theta. Now it has to be in radian mode to graph, but we like to look at it in degree mode to actually plot points because it's easier to go to 30 degrees. It is cool. And voila. Okay. Hey, these are the different types of polar graphs you're going to see. Write it down. Make yourself a little note. So there are circle types of graphs, and when you have a circle, it's going to be this form. R is equal to A cosine theta, and R is equal to A sine theta. That's the examples we just did. So if it's cosine, it's going to be symmetric over the polar axis. So the blue circle is a cosine example of that form. And now my brown would be an example of the sine. I don't know. Okay, because I don't know this well enough yet. No, because I don't know, you guys. Like I said, I don't know this stuff very well. At least I'm being honest, right? Yeah, no, I don't know. This is called a how do you say it? Lemon-scon. 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 I've heard people say it before, but I just can't remember how to. It's lemon-scon. That sounds so ridiculous. Lemon-scon. It's all like the same lemon-scon. Like my dad's name's Scott and Lemon. Lemon-scon. Okay. It has this form. Well, yeah, it's fine. So, it's a little stretched out circle, more ellipsy, but that's okay. If you have this form of an equation, you're going to get this infinity. So this is an example since this is symmetric over the pi-half axis, right? This would be a sine example, right, everybody? You see how it's a reflection if I stamped it across? Where cosines would look something like this. So it's an infinity sign. Lemniscon. Lemniscon. I'm pretty nasty. I can't say it. Okay, will you pronounce it for me? Lemniscate. Lemniscate. Let me show you a skit. That's what it sounds like. Let me show you a skit. Oh, I don't know. Okay, here you go. This type of polar cross is called a lemnicon. 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 You guys, this is hilarious for me. Stop me, please. You guys, he's getting more of a kick about how funny I think I am. No, it just sounds weird. Lemniscon. Lemnicons. Lemnicon. That's how you say it. Lemnicon. There you go. This is a lemnicon. Like a leprechaun, but a lemon-con. Lemnicon. It is a lemicon. Maybe. Doesn't matter. So, type of polar graph. Write this down. If it has this form, it's going to be a lemicon. So, I think it's lemicon. Now, it'll have an inner loop. It actually has an inner loop if you have this and it's a shifted sine function, which makes sense. It gives it an inner loop, and we won't get into it. So if divided by b is less than 1, you get this small inner loop. This one would be symmetric over the pi-half axis, so this must be an example of sine, right? Looking at the picture. And then this is called a cardioid because this looks like a heart. It's actually called a cardioid. So it looks like a heart. So it'd be starting at 0 and then ding ding, which it must be sine. Think about sine. Sine starts at 0, right? So that's definitely a sine function since it starts at 0. And then it's symmetric over pi-half axis. So if a divided by b equals 1, it's going to be a cardioid and actually touch down. This is called dimpled. Notice the little butt dimple isn't clear up to the polar axis. So to me, this is a cardioid because it touches here, but this is just dimpled because it doesn't come all the way up. It's not like a heart. It's just dimpled. It has a little dimple. How cute. A divided by b is less than 1, but if it's, it's greater than 1, but less than 2, you're going to have a dimpled graph. So you're going to, it helps to know these rules because then you can say like, oh, I have this kind of dimpled graph. This must be a sine as well since it's reflected over the pi-half axis. And this is considered convex if it's kind of, I couldn't draw it very good, but like that. If you want it to be more exact, look in your book. Convex, that's what convex looks like. If a divided by b is greater than 2, it'll be a convex lemicon. These are the fun ones. These are called rose curves because they have petals. So this is a rule it actually is useful to know. So if it has the form a is equal to sine of n theta, r is equal to a cosine of n theta, so we have an n in front of theta, then this will have 2n, so if it's even, it'll have 2 times n petals. So if it was, for example, r is equal to a sine of 2 theta, we're going to have 4 petals, because 2 is even, correct? So you times 2 by n, which our n is 2, that would give us 4 petals. So this is obviously, look at it, it's symmetric over the pi-half axis, so it's a sine function. You'll go out, interesting, obviously, think about it, if our amplitude is 3, that means this would be out to the 3rd mark right here. Does that make sense? If a was 3, our amplitude's 3, so think about that. We would be out at our 3rd tick mark here. So if we have r is equal to a cosine of 4 theta, we're going to have 8 petals, and it's going to be symmetric over the polar axis here for cosine. So ding, ding. What? The polar axis. Because you'll have this side, and then they will reflect over you. Like it. You'll have the top. You'll have the top. But yeah, I mean, it's just, I drew a rough sketch. But yeah, you'll just see that they are reflections. Like, do you see if I really stamped this up across the polar axis, it'd be the same? I didn't draw it perfectly. You get what I mean? The polar axis, ding, ding, down and up. Okay, if there's odd petals, then there's not many petals. So a cosine of 3 theta would be 3 petals if it's odd. So r is equal to a sine of 5 theta, there's going to be 5 petals. And once again, our a will be how far out we go. So if a is 10, we would be out to our 10th tick mark here on our polar axis. We're using our calculators though to generate this for the most part. Yeah, we're gonna. Okay. Oh yeah, sorry, that was way too quick. Good point. Will just made a good point. This couldn't be cosine. This has to be sine. So I should erase that and write sine. But why can't it? Because it would be reflected over the polar axis, which it's not. It's reflected over the pi-half axis. So this should be sine. Or we could just change the graph too. Okay, here we go. Let's do some examples here. All right, here we go. Let's do this one. Here we go. So 4 sine of 3 theta. Let's get a picture on our calculator of what this is going to somewhat look like here. How about 4 sine of 3 theta? Well, first of all, the information I gave you, isn't this a flower graph? Everybody? A flower graph, correct? How many petals are we going to have? 3. Cool. So we can literally, yeah. So honestly, at this point, it's okay to just use your calculator. So go to your table of values and maybe tell me what some of these are. So negative pi halves. No, let's keep it in degree mode. You know that's negative 90 degrees, right? Oh yeah, let's change it back to degree mode and then make sure our table's set. Do you need me to show you? Uh-huh. Oh, that's gotta be it. See, you guys are so good at technology. What she means is, look at my window. Do you see how our X min and max, is that what you mean, Amelia? I'm just not. Theta min and max. So this would need to be 360. That makes sense, because this is radian. That's in radian. Ooh. Okay, now. Mode. Let's see. Stopping. Well, it's because it continues, guys. That's the thing. Think about it. It's going to continue. Think about the unit circle. It continues, right? Just starts repeating, though. You know what I mean? No. Second table. Hey, are you guys able to focus now? Hey, go to your table of values. Hey, everybody, go to your table of values. At negative 90 degrees, what's my radius? No one? It's 4. At negative pi thirds, what should be right here, negative pi thirds. So that's negative 60 degrees. What's negative 60 degrees at? Okay, what about negative pi 6, which is negative 4? Okay, so what's happening here? So that would be going down to negative pi halves and then out to 4. 1, 2, 3. Oh, 1, 2, 3, 4, correct? And then over negative 3 pi halves and then out 0. So that's coming in like this. And then at negative pi 6, we're at negative 4. So wouldn't that be walking this way? Everyone? Negative 1, 2, 3, 4. Then at pi 6, what are we at? Which is, remember what pi 6 is, 30 degrees, guys. What is it? So at pi 6, we're out -2. Oh, it's +2. Sorry. What am I thinking? And then pi thirds, we're at pi thirds is 60 degrees, 0. What the? Okay. Right here? This was 4? Oh. Okay, so we're at 1, 2, 3, 4. So then it's going like this. Ding, 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 and ding, ding. Now, how was I able to draw it in? Because I know what symmetry looks like for sine. Does that make sense, everybody? You get enough points, that's good enough for me. You draw an okay graph, good enough for me. That's all I can draw. But no, that's what Mr. Roberts is having his class do too. All good? Yep, cosine's over the polar. Okay, cool. Let's do this one. Graph it, give me some points. So, 3 minus 2 sine theta. And then you can look at your little thing to see what kind of graph we're talking. Yeah, that's called a dimpled butt. Not a dimpled butt, just a dimple. I'm inappropriate as a teacher and I'm on video. Okay, dimple. Now give me some points. Hey guys, from here, do you guys know what you're doing? Then you just plot points. Do we good? Like, I don't know. I just want to give you time to go. I feel like you know what you're doing. You just plot points. Okay, so don't do this one or do. Okay, so like this, looking at your picture, let's graph some degrees. So maybe like over here, let's graph some degrees. So positive and negative, and then we can symmetry. So -90 degrees, where are we at? Tell me. -60. So your calculator's giving you this. You're doing this, guys. Remember, second table? See? Because you didn't type it in right. Nope, you didn't. Just kidding. Here we go. Look. 3 minus, did you put it in negative? Oh, it probably just does, yeah. Your window might be bigger than mine, so you just can't see the dimple, but once you plot points, you'll be okay. Okay, so now you're doing second table, so you're just plotting points here. Okay, here we go. Hit quit. You gotta quit. Or pull the batteries out of that dang thing. Hey, here. What's this point? -60 degrees. Okay, what about -30 degrees? Okay, and 0? And pi 6, which would be 30? What? Okay. Okay, let's draw that in. So we go to -pi ½ and we're out 1, 2, 3, 4, 5. We go to -pi thirds and we're out 4, 1, 2, 3, 4.7, a little bit less. Then we're out -pi 6 and out 1, 2, 3. More like this. Then more like this. Wait, 4, right? Am I doing okay? And then over 0. No, sorry. Yep, over 0 out 1, 2, 3. Cool. So it's coming in slowly but surely to that dimple. And then out pi 6, up pi 6, out 1, 2. There it's coming. And then out pi thirds, up 1.2. So up pi thirds, out 1.2. Oh, there's the dimple bad boy coming in. Okay. And then at pi halves, we're down at 1. And voila, there's the dimple. Now, don't we know since it's sine that it's then just going to be a reflection this way? A rough sketch is good enough, and you could be as exact as you want. Okay? Okay. Dimple butt. All right. Okay, we're all golden. You do the pink worksheet, that's it. So do you guys see it's really just graphing points using your calculator? This one's better than I thought, yes.
My homework, like I promised.
Good job.